Okay, I hope my voice is on. Okay. Physics. I love physics. Okay. This video is like 4 or 5 days late, but I'll just try to recap everything we learned in physics for the past, for the past topic. Electromagnetic induction. What comes to your mind when you hear electromagnetic induction? Electro means electricity. There's a current. Magnetic means a magnetic field. Induction, you make the electromagnetic field. I don't know what I'm saying. Why am I trying to make an intro? This is not a video. It is a video. Wait. Okay, you see this contraption next to you, and you're like, what the hell is that? That's what we learned. Yeah, I spent way too long making that. Okay, don't look at this. These are like, okay, yeah, those were like definitely not some tutorials on how to do that. Okay, so, let's first. That's not the right one. Yeah. Okay. That's not the right one. Pen. That's not the right one. Paintbrush. That's also not the right one. Is it pencil? Yeah, pencil. Okay. Now let's first start the recap on electro. I'm not writing the whole thing. On this topic, electromagnetic induction. So we have electromagnetic induction means you induce EMF, electromagnetic force, right? And so this thing means that when you have a magnet, so this is your north and your south pole, and then basically you remember your let me just turn my webcam on. Yeah. So you remember. So this is my right hand. This is my left hand. So you remember Fleming's left hand rule: father, mother, child. FMC: force, magnetic field, current. Right. So this is the one where you basically this is the one where you have your magnetic field, you have your current, then it makes a force. So the mother and child make the father. Wait, it's not like that. But that's when the force is the one that's being induced. Now this time we want to induce EMF, which means to induce the current. So this time we flip it. Don't ask me why. We flip it. So this time we use the right hand rule, where it's still father, mother, child with the same fingers, but this time we flip around because so basically the force and the magnetic field are the same, but the current gets flipped. See, the opposing current. Don't ask me why. It's just induced current is different. It's the opposite direction. So we use the right hand rule. Force, magnetic field, current. And when do we use this? We use this when the EMF or the current is being induced. Right? So basically we have a force, we have a magnetic field, then it makes a current. Wait, that was vulgar. I'm sorry. Okay, so yeah, we have this. We have a field. You have a wire thing. That was a really bad wire. And then we move it. I don't know how to draw movement on here. And that makes a current. Wow. Yeah, this sucks. Feel like an eraser. Yeah. You induce the EMF, right? And let me just rewrite that. Okay. Sorry, this is kind of chaotic. That's not the right brush. Induce. So this time it's electromagnetic induction. So you induce EMF / current, right? And so when you induce this, we want to care about two things. One is magnitude. It's so hard to write on mouse. What the heck? Magnitude. And you have your direction. we have magnitude, we have direction. So each of these depend. So you use a law for each of this. So the first one, if you remember, is Faraday's law. So Faraday's law, it determines the magnitude, right? So Faraday's law is that the magnitude of EMF. So the magnitude of the EMF. How do I write that? So this is the E. This is the EMF. This current is dependent on the rate of change of magnetic flux linkage. So EMF is proportional to rate of change of magnetic flux linkage. So what is magnetic flux linkage? Like, what the hell? That's like a long word. So, it is like a recap. So magnetic flux linkage is the linkage of magnetic fluxes. What is a magnetic flux? And why is there a linkage of it? So magnetic flux is basically, we have an equation where magnetic flux equals BA. I don't know if you're supposed to memorize. I don't think you need to memorize this. It's just to understand, because it's basically the definition anyways. So B, if you remember from the previous topic, B is gonna be your magnetic field. So this is gonna be the strength of your magnetic field, and A is, you guys say A is like area, right? So area. So what area? Is gonna be the area perpendicular to the magnetic field of B. So the area perpendicular to the magnetic field. So what do you mean the area perpendicular to this magnetic field? So this is why I have this. So you don't have to worry about the specifics yet. I'll go into that in a bit. But basically I'll show you. So imagine, so you see this thing, this square thing in the middle. That's the so your red is your north pole. This is gonna be your north pole. This is gonna be your south pole, right? And basically the current's gonna go to this side, from north to south. The magnetic field is gonna go from north to south. And this magnetic field, it cuts this wire thingy, and that's the magnetic, basically the magnetic flux, where basically this thing, where the field, so you got the, what the hell, I did not mean to do that. Yeah, basically for that one, you got this is the north, this is the south. And it's gonna cut this wire thingy to create the magnetic flux. And this, wait, sorry, I should have drawn the direction. But you get what I mean. This is the north, south, and it goes this. I cannot teach. I'm not a good teacher. What the heck? Let me just, okay, I can. North, south, wire, and this goes across this way. So it cuts the wire, and that's what makes the magnetic flux. So the area in this equation, the BA, the area, is the area is being cut, and it's gonna be perpendicular. So for example, right now, okay, let's just select my wire, let's just select objects. Right now, you see, so you basically, you imagine going from north to south, right? The thing is really just not cutting much. It's only cutting the sides of the wire. You see it? Yeah. You can visualize. I don't have a better way to show it. But basically, go straight. Basically, let me show you on webcam. Okay. Right, this is your north, this is your south. Goes this way. So I'm using the magnetic force, I'm hitting the wire. And the wire is perpendicular to the magnetic field right now. So the only thing it's hitting is this side, right? But when I have my wire and I rotate it, the y-axis, and I rotate it all the way here, for example, then the wire is rotated here. And this magnetic field, see, it's like giving a high five. It's like the whole thing is getting cut. So this is the maximum area that's being cut. let's revert that. I'm gonna show you the specifics in a sec, so don't worry about that yet. Just a demonstration right now. But yeah, so this is when there's minimum area, where it's only the size. This one, maximum area. Everything. It's area perpendicular, so it's everything. Okay, you see? Understand? I hope so. So the magnetic flux is a B times A. But it's the strength of the magnetic field times the area the magnetic field is going through. So what's magnetic flux linkage? The linkage part. So what does linkage mean? Linkage means the action of linking a state of being. That's such a bad definition. The existence or forming of connections between things. Yeah, exactly. Linkage. That's what linkage means. So basically, there's a link between different things. So what different things are there? So the linkage, you add N, which is the number of coils in a wire. So it's gonna be NBA. So imagine, okay, let's go back to this demonstration. So this wire thing, it's not just gonna be one wire, right? In a generator, there's gonna be multiple coils coiling across each other. I can just like, how do you duplicate? Let's turn off snap. Oh my god. Yeah, there's gonna be multiple coils stacked on top of each other, and that's what makes like how it works, right? But I'm just using one right now just for the sake of simplicity. So basically, magnetic flux linkage is like coil product. So magnetic flux is NBA player, coil, field, area, NBA, right? Number of coils times magnetic flux, which is the field times the area. Can I get? So now we have the equation of EMF. So this not equation you need to know. I don't think so. At least it's just like just to like understand, I guess. So basically now we have our EMF, which I'm just gonna make an E, right? So it's the rate of change. If we know this in math, so it's just D, rate of change, D dt of what? Of magnetic flux linkage, which I just described is N. Make it better, N B A. And there's a negative here. You don't have to understand why. Miss O didn't really explain it. Miss O did explain it. It's because of this direction thing, where basically it opposes direction. The negative means the direction, right? But I'll explain that more in a bit, I guess. Yeah. So this is your equation. You don't need to know this, but basically E is the rate of change. It's directly proportional to the rate of change of magnetic flux linkage, right? So basically this means that E is dependent on three factors. One is N, the number of coils, B, the magnitude of the magnetic field, and A, the area. So if they ask you a question, how do you make a bigger current? Then you can have three answers. One is you add the number of coils, you add the number of coils, you increase the strength of the magnetic field, so I use a stronger magnet, or you increase the area. So like, for example, in this case, you rotate, or maybe you just need a bigger wire, or something like that. I don't know. Yeah, so basically that's what Faraday's law is. You need to consider three factors: number of coils, field, area. Got it? Got it. That's part one, Faraday's law. Yeah. So now that's it. Can I like? That's not how it works. Okay. So basically, let me just use eraser maybe. This one. Let me just rewrite it down here. So I have everything in one page. Oh my god, I keep selecting the wrong brush. Okay, so E equals negative D dt. If you have any questions, just raise to me on WhatsApp. Because I have WhatsApp. Because I am a social creature. NBA. It's probably too late for you to watch anyways. Just watch during breakfast or something. Hi guys, if you're watching. Yeah. Yeah, that's your equation. And the negative is based on the direction. So how do you get the direction? This direction you use lens of Faraday's law, like Faraday's lenses law, right? Oh, you remember? Okay, so I already went through 3 things. Faraday's law, how you get Faraday's law, the right hand rule, the difference between left and right hand rule, and why you use this. And basically, this right hand rule gives you the direction of the current, right? This is the direction of the current. But why is it opposing? It's Lenz's law. So basically, if you can't remember, you see, I have 2 laws. This one is when induced. So basically, when the current is induced, the direction is opposite. But why? Basically, Lenz's law in your book states that direction of induced current it opposes the change in magnetic flux. It opposes the change in magnetic flux. So, yeah, that's why there's a negative in this equation. It's opposes, so there's a negative sign. Yeah. So basically, so magnetic flux is your, so how this works, give me a sec, I did not prepare. Okay, so how this works is basically, when you have, magnetic flux is caused by what? It's caused by a magnet. So let me just draw you a magnet. So this is the north pole, this is south pole. And I have a wire right here. So this wire, it will naturally generate the current, right? So this wire, we're trying to generate a current from it. So when the north pole is approaching, you want to oppose it, right? So how do you oppose it? Oppose is repel. So you put a north here to repel this north. So when this north is approaching, basically this induces a north pole, and so this induces a south pole, It induces a north pole, so that so this thing gets repelled. It won't repel the whole thing, obviously, because you're the one moving the north pole towards it. So it will just continue to move. But in that moment, it will try it's like chaperone approaching a stalker. Like, you can't do that. Like, the stalker is gonna continue anyways. I don't know what I'm saying. It's gonna try to push back. It won't. It's gonna try to push back. And so what do we do from that? So basically, I have this current thing, this wire, it loops around like this and goes. I don't know what I'm drawing. So basically, this one we use our right hand rule to see what happens. So this one, so father, mother, child, right? Force. So basically, wait, no, this one is not right hand rule. Sorry, this one is the right hand grip rule. So basically, this one we use this. So this is the direction. Okay, so you remember your right hand grip rule, where this one is like a solenoid, right? Solenoid, so it's a bunch of coils coiling against each other in like a tube-shaped thing. So right hand grip rule, recap, this grip will be the current, and this grip will be the magnetic field. This is for solenoids. So basically, we can use the magnetic field we have because of the north and the south that is induced to get the current, right? So basically, this one, we have our north and we have our south, and so we're gonna point towards the north. Now you're gonna tell me, what the hell? I thought magnetic field is from north to south. You're not wrong. Magnetic field is from north to south. But the thing is, this magnetic field, right? It is from north to south. But the thing is, this is like a magnetic field bar, right? So basically, if you draw the magnetic field lines out, then wait, let me just do the north to south down here. If you draw the magnetic field out, it's gonna be like a bar. It's not a bar, but it's kind of like a bar. This one's gonna go out, right? These field lines are gonna go out. These lines are gonna go in. Sorry, that's wrong. go in. However, and then this one, it loops all the way back here. So you're not wrong. It does go from north to south, right? It loops like that, But the field lines still go out from here, and that's the strongest thing. We're looking directly at it, so it goes straight out. It's like kaboom. So basically, you point at the north outwards. So that's your magnetic field. That's the strongest magnetic field. There is something pushing back, but it still goes up first before it goes back. Right? So you don't do like this. It's gonna be like this. Right? So that makes a bit of sense, I hope. So basically, yeah, this one goes out. And because of that, we use right hand grip rule. You think, oh, it's gonna be like this. You see on the camera, I don't know. Just try to follow along with your own hand, because the perspective's kind of messy. Yeah, so yeah, the camera slips, so yeah. I don't know how to. Yeah, so it's gonna be like just follow along with your own hand. Basically, because of that, the coil. Okay, this coil is kind of shit because you cannot tell whether it's going out. Where it's going, basically. So let me just try to draw it a bit more 3D. I don't know how I'm gonna do that. Oh shit. Yeah, so basically, okay. Basically, okay. So the coil is gonna go north, and it's gonna oppose up, and this is south. The coil will be like this, and then coils towards the back, right? And then coils again, like this. Coils towards the back, and like this. Yeah. Does it make sense? You go like this, then like this. Yeah. So basically, you got our grip. Now we find out, oh shit, it's like this way. So it's towards this way up. Right, so this is your coil. Should be. Yeah. So this is gonna make a current. So this is gonna connect to this battery thing. I mean, this is called a galvanometer. So what's a galvanometer? It's like an ammeter. It's used to measure the current, but the galvanometer is like a weaker ammeter, I guess. Basically, what it does is that it measures weaker currents, because this current induced is still current, but it's not like that strong, right? So galvanometer is like an ammeter, but just weaker. It's not that important. So yeah. So basically, the current's gonna go up through this loop, right? Gonna go down. It's gonna go down in here. Gonna go in here. It's gonna go in here, and then back up. So that's how the current's gonna go. So what does this galvanometer read? So I just read an A for the ammeter galvanometer thing. So basically, it's like a lever. You can visualize it as a lever. Basically, it just goes towards, like, starts from the side where the current passes through and ends on the side like this. So your induced current is gonna go in this direction, right? It's like an arrow. It goes in this direction. So your induced current is gonna be towards the right. Right. So yeah, that's basically Lenz's law. Now what about the opposite scenario? Let's get my eraser. Opposite scenario. Let me just draw this again. Why am I getting messages at this time? Who's awake? What the heck? Okay, the pace has slowed down considerably for this Lenz's law thing, because I was not prepared. I'm so sorry. Basically, we have our magnet, north, south, and then we have shit. That's useless. Yeah, and it goes into this galvanometer. And okay, so now instead of going towards, we move away. the north-south is gonna be pulled away. So, okay, so like your physics mind, you're gonna think, oh, pull towards means the current is gonna go this way. So pulled away, current's gonna go this way. Yeah, you're right. Yeah, you're right. So it's gonna go this way. But how do we prove that? Basically, when it's pulled away, it wants to oppose the direction of the magnetic flux change, right? So how does it do that? So this is moving away, so you want to pull it back. How do you pull it back? You attract, and what attracts north? You attract it with south. And now again, you can go into details if you want, but basically, just point towards the direction with north, like I just told you earlier. And you have this grip, and going towards the north. You have this grip, and it's gonna go this way. So basically, this way, which means that it's gonna go. Yeah, it's gonna go downwards, and it's gonna go here, past here, and so it's gonna go upwards towards here, and then towards here, and this is why the galvanometer shows towards this side. Yeah, Lenz's law. And similarly, if you switch the positions of the poles, you can kind of figure it out. Yeah, you can kind of. There are like 4 cases. You can kind of just draw it out and do the examples in the book. It's helpful, trust. Yeah, and okay, so yeah, this is the recap of the 2 laws, right? Now, some application questions in the book. I think we've gone. I think for Faraday's there's not much, but there's. Okay, this one I'm gonna run through later. Should I go through it right now? Or go through the generator first? Okay, I'll go through it right now. So a special case. Okay, so basically from this whole knowledge, you can basically do all the examples in the book already relating to Faraday's and Lenz's law. Okay, here if you wanna just pause the video, just try to make your own notes. Alright, I'm gonna make a new one now. So what I want to go through is actually example 6, because there's a very interesting thing where you have to graph it. I'm gonna kill myself if this video, if the audio is lost on this video. I'm not recording for like an hour again. Example 6 is page 115. Page 115, right? It has graphing. How the hell do you graph this? So, basically for this one, the problem is you have this coil of wires, and you drop a magnet through it, and this is gonna be north, this is gonna be south. Drop through it, and you have like a thing that codes the data. So so this one is a data loader. I don't know what symbol to use, okay? But I should have drawn that first, so I can Control Z. Yeah, you're gonna drop this through, and gravity takes its course, and basically you want to draw a graph of the induced EMF, so I'm going to make E, over time. And you have your units, volts, this seconds. And so when you draw this through, what happens? So first this one, if we want to use Faraday's law to get the magnitude, it's pretty hard, right? Because there's we use both Faraday's and Lenz's law in this question, I think. Yeah, we use both Faraday's and Lenz's law. So basically, so first we use Lenz's law to get the direction first, because we have 2 components, the magnitude and the direction. So let's get the direction first. So when we draw through here, first, because Lenz's law is direction of a current induced is opposing the change in magnetic flux, So this one, the change in magnetic flux, this one's the north, and it's coming through. So what you want to do is you want to make it go back. So you want to repel it. So this one's going to be an induced north, this one induced south. We use the triangle rule. It's going to go like this way, go like this way, go like this, like this way. Yeah, what am I trying to say? Basically, if you take this as positive, it's gonna go here, 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 and go like here, yeah. And so it's basically, it starts positive. Okay, I don't know if you can. Basically, okay, so at first it drops and then it goes this direction, right? Because this is the north, this is the south. But like later, when the magnet is dropping through, right? Wait, I'm not a good teacher, I'm sorry. Okay, yeah, when the magnet is dropping through, and it's like dropping through, and it's gonna be exit. Let me just erase this. It's gonna be exiting. At first, the top is north and the induced north, and the bottom is induced south, right? But then now when the let's go back, zoom back, bro. So now when the magnet is dropping through like all the way there, wait, that's not the right way. This is the right way. It goes all the way down like this because of gravity. This one, when it goes out, it want to impose, so it want to pull it back in. So this one actually becomes the north to attract it, and this one becomes the south. So basically, your right hand grip rule becomes from this to this, and basically that means it flips direction midway. So basically, let's just say it starts off positive, and it ends up negative. Right? How the graph's gonna look like? Let me just give you the answer right now, and see how you will interpret this. This is your graph. Right. Okay, what the hell is that? That's like so weird. So there are multiple things to unpack with this graph. So first, I just told you, start out positive and ends out negative. So why is there like this huge spike at both places? Huge spike. So this one we have to use Faraday's law because it's magnitude, right? So let's go through this. So let's just restart from the start, right? Oh my god, this video is actually gonna be 1 hour long. So this is gonna be your north, this is gonna be your south. So like I said, this is gonna be north to repel it because it's going down, and this is gonna be south. And so why is there a spike? It's because Faraday's law. What is Faraday's law state? EMF, and then it's proportional to change, rate of change of magnetic flux linkage. Change in magnetic, rate of change of magnetic flux linkage. So it's the change of magnetic flux linkage that we have to care about. My computer's gonna die. I have to charge it. So when we have the change in magnetic flux linkage, you have to understand, at first the magnet is nowhere near let's say it's nowhere near the wires, right? Then your magnetic flux linkage will be zero because you're getting no magnetic force. But then you suddenly get a magnet here, so like, whoa, I got a magnet, I got magnetic flux linkage. So the magnetic flux linkage suddenly increases really rapidly. And basically, as it goes through this first half, right, it increases damn rapidly, right? And so when the magnet goes from here to like here, it increases really rapidly, which is why we have this spike, this whole big spike up here. But then when it reaches like in the middle-ish, like, at this point, your magnet is kind of just staying inside, because let's say the magnetic field flux linkage it provides is 100, right? Just a random number, 100. So when it stays in here for a long time, your 100 will just stay to be 100. There's no change basically no change at this point. There's only major changes here and at the bottom. So basically when it's 100, there's like no change. Your change is gonna drop. your EMF is gonna drop to like 0, right? And like, you kind of makes sense. So at this point, it's plus. This upper point is plus. This point is like kind of 0, which is why it drops down here. And then this point, when it goes down, all the way down, like I said, it flips direction. So this becomes the north, this becomes the south. So it's gonna become negative, right? So this one's negative. But there's also a spike, because at this point when it's exiting, right, you're changing from like having magnetic flux to having 0 magnetic flux linkage. So like that's a big change, because you're going all the way down to 0, and 0 is like a very like big number ish, right? Yeah. So basically, okay, how do I explain this? Basically, okay, so imagine at this point, magnetic flux linkage is, so why does it spike when it's 0? Like, it's okay, let's say this point is at 0, right? Okay, no, let's say at this point it's like 1, and this point is like 1, right? So let's say at this point right here, your magnetic flux linkage you're experiencing is like 10. At this point, your magnetic experience is 10. At this point, like in the middle, it's gonna be 100. And right, because of the magnet and how much it affects the coil, the magnetic flux linkage. So like, basically, you're not measuring the magnetic flux linkage. The equation is not magnetic flux linkage. The equation is rate of change of magnetic flux linkage. So yes, the magnetic flux linkage increases from 1 to 10 to 100 to 10 to 1. And like, but like, it's okay, so basically, like, and at this point, let's just say you have like, so basically at this point, and then like, at this point you say it's like 20 or something, yeah. So basically, if you increase from 1 to 10, that's like plus 9 units, but let's just say plus 10 units, yeah. And this one is like plus 10 units, right? So you're gonna think, oh, the rate of change is the same, right? Because you're still adding 10 units, so it's gonna be the same. But no, the thing is, the rate of change is, it spikes. Why? Because it's easier to go from a small number to a slightly bigger number, from a slightly bigger number to a bigger number. Why? Yeah, what the hell are you talking about? Yeah, this part is kind of confusing to talk about. But basically, to go from 1 to 10, you add like 10 units. 10, I cannot do. It's 9, but let's just say it's 10. And to add from 10 to 20, you add 10 units, right? But the thing is, from 1 to 10, you're times 10ing it. You're multiplying it by 10. And from 10 to 20, you're multiplying it by 2. Like, if you think about it, the percentages, this one increased from this one. You're multiplying 10. That's like 100%. No, that's more than 100% increase, right? And from 10 to 2, you're doing it times 2, so it's only 100% increase. This is like 1000% times increase. Wait, an easier way to imagine it is like, it's easier to go from 1 to 2 than from 99 to 100. Like, the change is much greater, because from 1 to, so both is plus 1, but 1 to 2 is times 2, so it's plus 100% of 1. But 99, you're not even timing 2, you're like timesing 1.01 or something. So you're like only plusing like 1%. So like from 100% and 1%, it's like much different. So the rate of change actually, it drops over time. So that's why it spikes so high here, because it's going from 1 to 2. At this point, it's going from 1 to 2. So that's why there's a spike, because the rate of change, it's so significant, because no matter how little you impact it, like, it's just going from 1 to 2, but the change is so massive because it's like 100% increase. That's why there's a spike. And at this point, there's a spike because you're going again like from 10 to 1, and because of that, it's like, oh, you're playing from having some to having none. So that's why it's another spike, because at here, because the rate of change, it's like again, it's easier to go from 2 to 1. I mean, there's more effort to go from 2 to 1. It's more significant going from 2 to 1 than from 100 to 99 at this point, right? Because it's 100%, this is 1%. And that's why there's a spike. These two spikes are at those points where they just entered the thing. And then it goes back to zero. Why? It's because when the magnet is removed, there's going to be no magnetic flux linkage. So your induced current is going to be zero. So that's how you get the graph with that. However, there's another scenario of the graph where it's basically the same thing, It's basically the same thing. But do you understand this? Okay, if you don't, I'll try to make clearer explanation if you text me, just clarify any doubts. So this time, if the solenoid is really long, so basically you have two stages. In the middle, it's here, so at zero, and at each point where it enters and exits, there's the peak. That's the main thing of the graph. But the thing is, if the solenoid is really long, the magnet is going to stay in the middle really long, and it's just going to affect the thing by 100 of its capacity, all the time. So, but there's still a spike at the end and start at a spike at the end. But in the middle, when it stays for too long, there's going to be a segment where it's just going to be zero, because there's no change. The magnet is in there, and it will always be in there. There's going to be no change. And then there's a spike. So yeah, the graph will just look at that. It's just a bit extended out here. Okay, so that was a mouthful. I need water. Yeah, that might be a bit hard to explain because graphs are kind of abstract. But yeah, I tried my best to explain it. Just clarify any doubt. We've reached the 40-minute mark of this video, and I still have AC generators to cover. Okay, so basically that's Faraday's and Lenz's law. So recap again, Faraday's law. So basically, for this topic, we use magnet, and we use what? We use magnet, we use force, and we induce a current, right? So which is why we use right-hand rule. And so what we care about the induced current is two things: the magnitude and the direction. And the magnitude depends on Faraday's law, where what was it? Faraday's law states that the magnitude of the induced electromotive force, EMF, is directly proportional to the rate of change of the magnetic flux linkage. Yeah. So in magnetic flux linkage, it depends on number of coils, the magnetic field, and then the area perpendicular to the magnetic field. Okay, so that's Faraday's law and Lenz's law. So the other thing, we got the magnitude, and now we have the direction. And the direction is the Lenz's law. So the Lenz's law means that the direction of the induced current, induced EMF, whatever, it directly opposes the direction of the change in magnetic flux linkage. Like in the form of a magnet moving towards it. Something like that. And how you explain it is because when a magnet comes towards it, like a North Pole comes towards it, then when it comes towards it, it wants to repel, wants to push back against it. So what repels north? North. So it's going to make a North Pole. You use a right-hand grip rule, figure out where the current is. It's going to be in that direction. Very quick recap. Okay, that's Faraday's and Lenz's law. Now for the big topic, AC generators. Now you're gonna look through your book and you see there's gonna be no AC generators. What the hell are you talking about? It's not in the book. And you're right. It's not in the book. But it's gonna be printed out because they say they're adding it in the book. Like, what the hell? Yeah, they're gonna give us separate notes for this. I don't know why. I love our physics department. They just keep adding new stuff. So yeah, basically AC generator. So what does this remind you of? So AC, what does it stand for? It stands for alternating current. Alternating current. Why is it alternating? I'll show you in a bit. But this is opposing to direct current. right? And that's DC. So we've learned DC circuits the last topic, where there's the split ring commutator, and you spin it, it changes every half around to create when the current goes through, it creates it creates a constant turning force. Like it creates a DC motor, right? It creates a constant turning force. So what the AC generator does, so the DC motor, it makes a force, it makes a turning force, right? Because it's a motor. The generator, it makes the current. And then you're gonna ask me, you have the father, you have the child. Where's the mother? Magnetic field. What's gonna make the magnetic field? To that I reply, the secret MC current. It's the fucking magnet. I'm so funny, right? Magnet. I don't know what I'm doing. It's getting too late. So basically, DC motor makes the force, turning force, and AC generator, it makes the current. And how does it make the current? Where's the hell right there? It's the alternating current. Wait, let me just write that down again. Pencil. And how does it make a current? That's why I make this diagram. Wow. So basically, this is completely contrasting to DC circuits, right? But it looks similar, right? So this your AC, so you got your magnets, your north and your south pole, it goes from north to south. And you got your wire, and the wire, it turns like this. Okay, it doesn't turn like that. It turns like shit. My camera's kind of awkward for this. It turns like this. So you think it's the same thing, right? But the main difference here is these two rings. So for DC currents, so I just write. I should write. I just keep it as. My God. Oh shit. Sure, that works. Can I just draw? Yeah. What the hell? Anyways, yeah. DC, this uses a thing called a split ring commutator, right? So basically it's split. So the ring, it has this hole for the thing to hold inside, right? And this is how the current, it flips between the sides, because at first it's gonna be like this, but when it turns, gonna keep turning, and then the wire, it flips to which ring it's connected to, right? But this one, the AC, use something else. Sounds similar, but this one's gonna be the slip ring. Slip rings, let's just say that. The slip rings, they're two completely different rings, but this time it's each connected to a fixed wire. So for example, I have this red slip ring here, and it's always gonna stay connected to the red half, even if the even if the red half, it turns, it's still gonna stay connected, right? Yeah, even if the red half turns, it's gonna stay connected to the red half, and the blue slip ring also is gonna stay connected to the blue half, right? And so what this does is that it allows the same current to flow through, no matter what. Why is this important? It's what makes the alternating current. I'll explain more with this contraction. So okay, imagine the slip rings, they have other wires that connect to a battery, or a galvanometer. A galvanometer. Gonna connect to the galvanometer, which is gonna allow us to measure the current, right? I was drinking water, sorry. So how this works is that, so for DC current, DC motor, we run the current through, there's a magnet, and then we get the turning force. For this one, we have the magnet, but this time we apply the force. We turn this. We turn this. We turn it ourselves. So we rotate it, and this makes a current. So how does that work? So we use Faraday. We use the. Let's just use the right hand rule to like illustrate. Okay. So at first, let's say so let's say turning motion is this way. So at first, the red side goes up. Right? At first, the red side goes up. So first the red side goes up. So we use the right hand rule. You just get the direction. And yeah. At first it goes up, so the force is upwards. And then the magnetic field is towards from north to south. So it's towards the right. So father and mother gonna go towards here. So your current is gonna go to here. So basically your current is gonna go from red to blue. And if you try to do from the opposite side, the blue is gonna go down, and the field stays the same, so it goes out. So basically, yeah, the magnetic, we just verify at first, when red goes up, the field's gonna go from, the current's gonna go from red to blue, right? But as this continues to rotate, then at this point, your red. Wait, let me just make a new sketchpad note. So at first, why are people still texting? So at first, it's gonna go from red to blue, right? Because the red side is moving up. But at this point, the red is moving down. It's moving down, right? Moving down. And the blue side is the one moving up. So at this point, your red, let's just take the red as the focus point. Red is gonna go down, magnetic field still this way. So your current is towards this way. So your red thing is actually going outwards now towards the ring. And the blue, if you do, so blue's moving up, magnetic field, and current's gonna go here, and it's gonna go towards the red. It's gonna go inwards towards the red. So after the rotation, it's gonna go from blue to red. And the thing is, the turning force stays constant, so it still continues to turn in this way of I need to find a better way to do this, bro. It's still gonna continue to turn this way, right? And basically what happens there is that because of this, this stage it goes from red to blue, then this stage it goes from blue to red, red to blue, blue to red. This is what makes the alternating current as it continues to spin. This is what makes the current alternating. So basically it's gonna so let's just say the red direction is gonna be positive and this is gonna be negative. So your current is gonna go from negative to positive, negative to positive, negative to positive. And what graph does that remind you of? So this one we have the graph, how the EMF looks over time. Well, in math we have this sine graph. And this is basically gonna be, and it's gonna continue, whatever. This is gonna be the graph of your AC current. And like, why is it a sine graph? Why is it not just like, I don't know, just like this, and it goes down here, go down here, go here, here? Why is it not just straight lines, right? Well, it's because, okay, so for this one, we got the direction already, right? Because from the right hand rule, we got the direction. Now, shit, I need to draw it again. Now we just need the magnitude to explain why there's a sine graph. Let's just revert this, my end panel, rotation, Y, let's just put it back 90, wait, oh, it's not focus on everything, whatever. Oh, it's because it's focused on only one object. Yeah, I need to find a better way to group this. Anyways, I'll figure that out with another Blender tutorial sometime. So basically, let's rotate this back to the. Oh, not like that. As close as I can get it. Yeah, so basically it's like gonna be like that. So yeah, so this is gonna be the initial position, right? So I already told you before, like you remember, this is gonna be your magnetic field. Wait, this one is a bit flipped because I flipped the direction. Yeah, it's gonna go from right to left because yeah, I can just use my other hand. What the hell? Yeah, it's gonna go from left to right. So this is gonna be my wire, and this is gonna be my magnetic field. It's gonna hit this side. It's gonna hit a very little portion of it, right? So this means, so you remember your magnetic flux linkage is NBA. So number of coils, magnetic field, and the area. So the thing we're thinking about right now is the area, because the magnetic field stays the same because we're using the same magnet. Number of coils using the same because we're using the same wire, right? So the only thing to consider is the area. So at first the area starts at let's say it just starts at 1. Now at this point it's gonna be like this. And so it's gonna be like this. Oh, you're cutting a bit more because you're cutting a bit more down here, right? So you're cutting more than this, where it's just like this small section. You're cutting a bit more. Make sense? You do this with your hand. It's kind of easier to understand. Basically, this hit is gonna cut a bit more, right? Gonna cut through a bit more. So basically, your area, let's just say it increases 10 again, or yeah. And this one, select objects, and this is the maximum position, right? So this one is gonna be the maximum area, right? And so it basically goes to 100. And we continue rotating. This one back to 10. This one back to the original position. So it's gonna be back to 1. And it's gonna do this over and over and over again. I'm just considering this part right now, by the way, because this part is the same but flipped. So this part is gonna be 1. This part is gonna be a 10. No, 100. 10. 1. Oh wait, this axis is time, but let's just think of it as the part where it's area right now, okay? So basically at this part, it's gonna be the wire is gonna look like this. This part the wire look like this. This part wire back like this. This part wire back like this. And this part wire back like this. Right? Yeah, so basically those are the peaks. So you're gonna ask again, what the hell? I thought this one means, wait, sorry, I flipped it. This one is like this, sorry. Yeah, this like this. This is like vertical like this. This is gonna be like this, like the horizontal. This is gonna be back to vertical. Gonna be like this. So yeah. So the graph actually starts like this. Sorry, like this, and it goes to the peak, goes to the bottom again at the 0, goes to the peak, and goes to the 0. So this vertical thing is actually where the 0 is. This vertical thing is where the EMF is actually 0. And I was like, why the hell? Because this one's supposed to be the maximum area, like 100 area, right? It's gonna be 100 area, so why it's gonna be maximum area? Because like it's high five, it's the whole thing. So why isn't it the peaks? Why is it the 0? It's because at this point, like I said before, it's easier to go from 1 to 2 than from 99 to 100. It's both change in 1, but 1 is way more significant than the other. This one 100%. This one 1%. I told you. So at this point, when it's 100, if you change it a little bit, it's still gonna slap basically the same thing. It's just gonna change a little bit. This one, you change it. This one when it's flat, change it a little bit. Oh, suddenly there's area to hit now. There's more area to hit. It's way more significant. Which is so because this one is dependent on the rate of change, right? Faraday's law, EMF dependent on rate of change of magnetic flux linkage. So basically, you have to care about the rate of change of the area. So right now, when the area is a lot, you change it by 1 unit, it's not going to change by much, which is why it's so little. But this point at the peak, it's at like very small, like 1. You change it by 1 unit, that's 2. That's already very significant. So which is why the gradient is much higher. And then it goes back down to the 0, down like this, like this. Oh my god, my throat is getting so dry. It's been 1 hour already. I hate physics. If you made it this far, you're insane. Yeah, that's the AC thing. So basically, at this point, when the area is very high, you change it by just a little bit. It's not gonna make much of a difference. But this point, when it's vertical, change it by just a little bit. It's gonna be very, very significant. Which is why the EMF produced is gonna be very, very significant. Because of Faraday's law, which is why the magnitude is like this graph. You're gonna have to graph this. So that's why that's how AC generators work. You generate the current, and the current is gonna be an alternating current because first it's positive, and second it's negative. Right? So then you're gonna ask, like, why? Why use an alternating current? Why you have to go from positive to negative to positive to negative? Is that you think in your head, like, if you like use it for a machine, wouldn't it just like flip back around? And you're right, yeah, the current's gonna be kind of weird. It's like it's gonna go this weird direction where, it's like, imagine you plug it into a light, like a light source. You got your AC generator here, plug it into a light source. It's gonna go from positive to negative, right? So it's gonna like go from very bright, like plus brightness, to negative brightness. Like, you're gonna think, what even is negative brightness? It cannot get darker than 0, right? Or so go from positive brightness to negative brightness. That's not possible. But then I tell you, the plus and minus is the direction of the current. When you power a light source, it doesn't matter if your current goes from this side to this side, or go from this side to this side. It just cares about the magnitude, because it's gonna care about the brightness. So it's just gonna stay bright, no matter if it's this peak or this peak. There's no negative brightness. It's just gonna stay bright. But you're gonna ask me, what are these 0 points? Will it just flicker? And I'm gonna tell you, yeah, it will flicker. But the thing is, this thing usually it curls so fast that you just don't really see it flickering. If you like slow it down, then sure you might see it flickering. But then, does it really matter? It's still generating electricity, right? So that's what it's used for in like power sources like that. You're gonna tell me, but then, what if we just want like the graph to be always positive? Like, you always want the same direction current, and yeah, that's technically possible. So what you're gonna tell me to do is like this, flip like this, and then alternate like this, like your DC current, where your current not like this, because the force still stays the same. But you're gonna tell me like, just flip it like this, and you're gonna have the same direction current no matter what. And I'll tell you, yeah, you're gonna have the same direction current. That is true. But it's just like not necessary, and it's just not worth the trouble, because who the hell is gonna turn it like manually like this? You have to find a robot to like actually do this, so it's like more trouble than it's worth. You just do this, it's gonna create a current, and most of the time you're just gonna care about the magnitude anyways. There's just some extra stuff you don't need to worry about. Like, I'm just gonna talk about this because why is AC generator important? So yeah, that's how AC generators work and how it's important. Yeah. Oh, this is taking too long. So yeah, recap about AC generators. AC generators create an alternating current, so it goes from positive to negative, positive to negative. How it works is that there are these slip ring commutators, slip ring SLIP, that allows each half of the wire to be constantly connected to these slip rings in the same half of the current at the circuit, as opposing to DC, where it makes the wires slip. The split rings makes the wires like change halves every half a turn, right? Yeah, and this generates an alternating current. Right, it generates the current. Yeah. I would make a recap of Faraday's and Lenz's law again, but this video has been 1 hour, and I kind of want to sleep. I don't want to drag it out for too long. So, my throat is dying. And yeah, recap. Faraday's. What did we learn today? Faraday's, Lenz's law, Faraday's rule, Lenz's law. So that means left hand rule, right hand rule, and your AC generators. Do your notes. Do your homework. I don't know. God. I should get paid. Why am I still getting messages? Holy shit. Okay. Good night, everyone. It's 12. I need sleep. Goodbye. I'm gonna crash out if this has no audio.